These are the notes for 3.1, Measures of Center. We have two goals today: calculate the measures of center, mean, median, and mode for data sets, and use summation notation to express the mean. So that's the new notation piece. So we have starting off with a definition here: descriptive measures that indicate where the center or most typical value of a data set are called measures of center. The definition for mean, then we're going to talk about mean, review here, and then we'll share some new notation for it. So we have the definition is the sum of the observations divided by the total number of observations. So it's also known as the arithmetic mean. So here's an example. We have weekly salaries. So Professor Hassett spent one summer working for a small mathematical consulting firm. The firm employed a few senior consultants who made between $800 and $1,050 per week, a few junior consultants who made $400 and $450 per week, and several clerical workers who made $300 per week. The firm required more employees during the first half of the summer than the second half. Table 3.1 and 3.2 list typical weekly earnings for the two halves of the summer. Find the mean of each of the two data sets. So we're going to do that how we already know how to do that, by just adding them all up, dividing by how many there are. So 300 plus 300 plus 300 plus 940 plus 300 plus 400. I skipped a 300. So 300, 300. Another 300, 400, 450, plus 800, plus 450, plus 1,050, and then divide that by how many there are, and we have 3, 6, 9, 12, 13. So our average, the mean for this data set, I showed you, take a look at the other, that's a start. Take a look at the other video for how to calculate that quickly using your sheets, Google Sheets. So the mean of data set 1 would be, add these all up, we get 6,290 divided by 13, which is $483.50. Similarly, if we do data set 2, add these all up, we get 4,740 divided by the total, which is 10. So we get $474 on average for data set 2. Yes?
So where did you get the 4,000 and 6,000?
I added up each individual observation. So just by adding up 300, 300, 940, yeah.
And then you, so once you get your number, you divide it by how many in the table?
Yep. Great. Thanks for clarifying. So then a key part of this that kind of may be a new element to the process of finding measures of center is this interpretation piece, just reconnecting it to the real life scenario. So the employees who worked in the first half of the summer earned what? Blank on average than those who worked in the second half. More or less. Those who worked in the first half of summer great. So we're comparing this number here was the first half of summer to this number here, right? So that's kind of like an added step that we were not used to, thinking back over the scenario and being able to clarify the meaning. Now I'm going to throw in our new notation. Exam scores, so we talked about that as being one of the goals. We have these 4 exam scores. And we're going to represent each one of those exam scores using our new notation. So individual exam scores, I would use the variable x to represent the exam scores, and for each different exam score, I'm going to give it a different subscript. So x sub 1, I'm going to say equals 88, x sub 2 equals 75, x sub 3 equals 95, and x sub 4 equals 100. Super basic, but this is new, a new way to do it. The next part says use summation notation to express the sum of the 4 exam scores. So summation notation is this symbol. It's sigma, capital sigma from the Greek letter S. So I would be adding up. It just means add up all of the values that follow. So x sub 1 plus x sub 2 plus x sub 3 plus x sub 4. So in other words, we could say that equals 88 plus 75 plus 95 plus 100. We're just representing using that different notation. The subscripts don't necessarily indicate order, but rather they're just a way of keeping observations distinct. So just to reinforce that same process, summation notation is the uppercase Greek letter sigma, shorthand for the sum. The letter sigma corresponds to the uppercase English letter S, used here means, literally translated, the sum of. So again, in place of x sub 1 plus x sub 2 plus x sub 3 plus x sub 4, we can just use summation notation, reading summation x sub I. So the sum of the observations of the variable x. So that would look like the sum, the sum of all of our x values is a shorthand way to write what we just wrote in the blanks there. So, for example, we have that exam score data, and we have adding all of these up. So we could say x sub I, kind of missed the blank there, sorry about that. X sub I, the sum of x sub I is equal to the sum of each one of these values, which can be replaced by those specific observations, those specific numbers. So the values of a variable for a sample from a population are called sample data. This distinction is going to become very important as we move through Unit 3. The mean of sample data is called a sample mean. You can see outlined here, we have the definition for sample mean. So we kind of have converted just that basic definition from page 1 into the notation of this key symbol here. You see it a ton over the coming unit. It's the way to read it is X bar. We call that X bar, and it is the shorthand representation of the phrase sample mean. So as we do as mathematicians, we replace phrases with symbols. So this is a new one, but like I said, you'll get used to it. It means sample mean. And then you have the definition, all of those words replaced with symbols, the sum of all the x values, of all the observations, divided by n. What is n? N is the sample size. So however many there are, right? It's great. It's a great way to abbreviate. We just have to get used to some new notation. So children of diabetic mothers, the paper correlation between the intrauterine metabolic environment and blood pressure in adolescent offspring of diabetic mothers. So this is straight from the Journal of Pediatrics. We typically use those for data sources. We typically find those to be reliable. And then it presented the findings of research on children of diabetic mothers. Past studies show that maternal diabetes results in obesity, blood pressure, and glucose tolerance complications in the offspring. Pretty interesting. Table 3.5 represents the arterial blood pressure in millimeters of mercury for a sample of 16 children of diabetic mothers. Determine the sample mean of these arterial blood pressures. Let X denote the variable. Here I have to reference arterial blood pressure. You can join in. But I'm recording. And table 3.5 got left out. Sorry about that. So basically, I'll just give you the values here. X bar is equal to the sum of, so practice writing these in. I'll make this go a little bit quicker. X, the sum of all the X values divided by N. I'll share that with you just straight out of the book so you can kind of catch a glimpse. This is table 3.5. So you can see we're going to add up all of these arterial blood pressures from the 16 children. All of these here are going to add up to 1,378.9 divided by 16. So our sample mean, so this is the sample mean, right? Every baby of a diabetic mother is born with a blood pressure, and we can't possibly know all of those. That's why we take samples. So the sample mean here would be 86.18. We're going to move on now to the median. So the median of a data set, we know what the median is typically. We're familiar. It's the middle. I think this chart here is super helpful just because it reminds us what to do when you have two numbers in the middle. So we arrange the data in increasing order, and then if the observations is odd, there's a middle number, right? It's very obvious what the median is. It's exactly the middle number. And if the number of observations is even, the median is the mean of the two middle observations in the ordered list. So in both cases, if we let n denote the number of observations, then the median is at position n plus 1 divided by 2 in the ordered list, which is kind of a convenient formula to remember. You just take how many, remember n, we just defined n above as the sample size, right? N is the sample size. Add 1 to that, divide by 2, and you'll be able to, if you just line them up, rather than doing the kind of cross out method and find the middle, you can just count down the line to that number, find the middle. So find the median of the weekly salaries from table 3.1 and 3.2. We have the median, we have to line them all up in order, which is, go ahead and write those out, which is already 300, how many 300s do we have? 300, can anybody tell me?
6.
Thank you. 6, and then we've got some 400s, so we can cross out all those 300s. And then we have a couple of 400s in there. And then we have a couple 450s in there. And then we've got 800, 940, and 1050. Like I just mentioned, you could go through and do the cross-off method. This isn't a super long list. Or we could just realize how many observations we have here, which is still 13. Add 1 and divide by 2. So we could use this process here and say 13 plus 1 divided by 2 to find the middle is 14 divided by 2, or 7. So I could just count down 1, 2, 3, 4, 5, 6, 7, and boom, I found the middle. I find that to be a little bit simpler than trying to do the cross-off method, right? Especially as our data sets get large, which they are going to get large because we're in the practical framework of statistics, and we're not just kind of in the imaginary world of abstract math in this class, and so we should have larger data sets. If we have really small data sets, we're not really getting a good glimpse of kind of what we could use to interpret the population. So we found the median of that set, and next we're going to find the median of that second data set. So 300, how many 300s do we have here?
4 or
5? Thanks. And then we have 400. I always start over too far. 400, 2 400s, a 450. Still have that 940 and 1050. So now this time we have the 10, right? We have 10 data observations. We have to add 1, divide by 2. So that gives us 6.5. This is the even set, so you guys see a little bit of both. We count down 1, 2, 3, 4, 5, 6.5. So it's halfway between 400 and 400, which happens to be, if you add those up and divide it by 2, 400. So when we're looking at the median of these two data sets, we find that they are the same. I made a separate video so that I could do a screencast question. It's not, when I said 6.5, I meant 5.5, which will put me right here. Thanks so much. Just see if you're paying attention. So glad you were able to catch that, because we would have been way off. 350. The prize goes to Mr. Sawtelle today. I made a separate video, like I said, for using technology to calculate the mean. Google Sheets is a best friend here, which you have access to in any practical life situation. Take a look at that video. You're just using the function average, similar to how we use the function sum of in our previous unit where we were talking about different sampling methods. Pros and cons to mean and median. We have the mean is not it is not oh goodness, I'm forgetting the word. Well, what's the word? Immune, like, yeah, we're going to just say immune. To extreme observations, right? It is affected. It is not so impacted. It is not impacted, immune, whatever you want to say there, to extreme or very large or very small observations. The median is immune. So cross out the word not. That was a flip-flop there. So therefore, when you've got these extreme observations, you want to use the median. That's going to give you a better measure of center. So here you have our curves again, distributions is the word, of these different data sets, and it's comparing where the median and mean are located in relationship to one another, given these different distribution shapes. So if you're right skewed, remember that's where you have that, you would have an extreme larger value. The median is to the left of the mean. When you have the symmetric data set, so you have all of the data kind of evenly distributed around your mode, right? The mode is where that tops out. The mean and the median are the same point. And then when you have left skewed data, your mean is going to fall to the left of the median. So with the mode, we're going to talk about the weekly salaries and determine the mode of each of the two data sets. Now the mode, I think, is the simplest one. The mode just means the number that occurs the most often. So take a look at 3.1. I think we kind of even just writing them out to find the median and finding the mean. It was very obvious. The number that occurred the most one in data set 1 was 300. And for data set 2, it was also 300. There's a video as well, in that video about calculating the mean using technology. There is discussion about calculating the median using technology. Again, it's not hard to line them up in order and find the middle. It does just take time. So let's use our shortcut, use our resources, and use that function median, similar to how you use the function average. And that concludes our notes on 3.1, measures of center.